All right, welcome everyone to today's a16z crypto research seminar. Very pleased to introduce Elaine Shi, full professor at Carnegie Mellon. Elaine's worked extensively in almost every area relevant to blockchain technology, whether it's cryptography or consensus or mechanism design. She's won lots of stuff, Sloan Fellow, Packard Fellow, et cetera. Very happy she's here to talk to us today about accessing data privately. So.
Yeah, thank you so much. I'm very excited to be here today. I'll talk about how to access your data privately. So I'll start with some motivating examples, like why real-life applications really need this. And I'll start with Signal's application. So Signal is running private contact discovery. And what happens is, like, let's say Tim wants to join Signal, and he wants to discover his friends on Signal. So he's going to send his address book to Signal, and Signal will return the entries corresponding to his friends. There's like various application domains where this happens. I'll start with the Signal example and say like why access pattern leakage is an important problem, and now I'll quickly go over the other applications. So with Signal, obviously, you know, Tim thinks his address book is top secret, so he doesn't want to disclose it. And one solution to this problem is we can use trusted hardware, also called TEE. Essentially, you can imagine there's like some hardware sandbox. Everything's encrypted, either in storage or in transit. And data can only be decrypted inside this sandbox where the computation takes place. So the problem with this solution, like, it appears that it should be very secure because all the data contents are encrypted. But the problem is that here only the data contents are encrypted, but the access patterns are not encrypted. And the access patterns are very leaky. In this particular example, if you observe which entries are fetched, it will directly leak who your friends are. So also, this should not be dismissed as a side channel leakage because this is like directly observable digital information that leaks your sensitive secrets. So that's one example. And then a similar problem also manifests in many blockchain applications. I'll just talk about one particular application, private order flow. So today what happens is that all the transactions are submitted in clear text, and then the block builder will assemble the next block to be included in the consensus protocol. The problem with today's approach is that the block builder can perform front-running and back-running attacks. So I gave the talk earlier to a crypto audience, but to this audience, you know, this is called MEV. And it's a big problem in the cryptocurrency community because this is actually causing the infrastructure to be highly centralized. So according to a recent empirical measurement by Yang et al., they show that more than 85% of the blocks are produced by just the biggest two block builders. So it's kind of like a duopoly. And obviously, if you are a blockchain creator, this is a big problem because the core value proposition of blockchain is the decentralization, right? So it is very important to retain the decentralized nature. And one envisioned solution is called private order flow, where users can submit their transactions in encrypted format, and the block building takes place in an encrypted fashion. Okay, similarly, in this context, the problem is as you build the block, you have to speculatively execute these transactions. So you can think of each transaction as a small smart contract program. And as this program executes, it's going to read data that lives on the blockchain. And these access patterns here are just equally leaky because they leak the crypto assets you are interested in trading. They leak your trading partners, and they also leak who you are. And this is precisely the information we want to hide. So therefore, it's also incredibly important to protect access patterns in this context. Okay, and it's not possible to give a talk without mentioning AI and LLM. And in large language model, a commonly used technique is called retrieval augmented generation, or RAG. And what RAG does is that it will take the user's query, it will perform some transformation on the query to figure out in this very large knowledge base which parts I should read to answer the user's query. And again, here, you can imagine the access patterns leak highly sensitive information about the query itself. So these are some of the high-value applications we are looking at, and they all ask more or less the same question. How can we provably defeat access pattern leakage but still preserve the efficiency? And I'm going to quickly formulate the problem. Imagine there's a client and there's a server. The server has a database. It has been possibly it has been pre-processed, and we are going to assume the server is untrusted. So what do I want? I want a protocol such that when the client wants to access some address X, the client and the server will interact with each other in this protocol, and at the end, the client will output the desired entry. And the security property is that we want to make sure, given any two access sequences of the same length, let's say X0 and X1 are two access sequences, I want to make sure the server's view are computationally indistinguishable. So the server basically learns nothing from its view about your intent. Okay, so there are actually a couple solutions that can solve the problem, and I'm going to compare them and tell you where things are today, and then look forward to the future. So I'll talk about two main techniques. One is called Oblivious RAM or ORAM, and the other is called Private Information Retrieval or PIR. Both of these techniques can hide access patterns. So what are the main differences between the two approaches? And I think perhaps the biggest difference is that ORAM allows per client state. In other words, the server is allowed to store a separate copy of the database for each client. Whereas for PIR, we typically assume all these clients want to access a globally shared database, and we don't want to make a separate copy of the database for each client. Like the database can be huge, like the blockchain, and it's like not viable to make a separate copy for each client. So for this reason, actually, ORAM is actually a better fit if we are in an outsourcing scenario. Let's say these businesses, they each have their own private data set and they want to outsource the data set to the cloud. Whereas PIR is actually better suited for accesses to some public, actually, it doesn't have to be public, it just has to be a global database. Okay. As you have seen, right, the motivating examples I talked about today, actually, they're kind of more like in the PIR bucket. They have a globally shared database. So why is ORAM still relevant? But let me tell you why ORAM is still relevant. So actually, the practically deployed solutions today, they actually use TE plus ORAM. And in order to avoid the drawback that the state has to be replicated for each client, essentially what happens is they have a TE in the cloud, and the TE acts as a global client on behalf of all clients. So this circumvents this problem. And this is the solution that Signal is running. Meta actually has also implemented ORAM with TE. They have open source available, and they told me they're going to launch some service based off it. And I asked them for more information, and they just say, okay, wait for the launch. Okay, and then we are also working with like blockchain players like Ethereum, Flashbots to get this kind of solution deployed. So it doesn't have to be TE, right? Like I think at this point, a lot of people will ask, TE may not be a good assumption. And especially, for instance, blockchain, like they believe in decentralization. They don't want to trust any single hardware vendor. So in the longer term, and perhaps it doesn't even have to be the longer term. Like you can think about replacing the TE with like a two-party computation or multi-party computation. In this talk, I'm only going to focus on two-party, but everything I say will apply to multiple parties as well. So here, essentially, you are using this 2PC to realize a cryptographic computer that replaces the TE. And of course, the third approach is just to use PIR itself. Okay. So I want to do things in a reverse chronological order. Yeah.
Just a question. So you care only about reads or reads and writes?
Reads we can do. I guess okay. Maybe that's a good question. Like I think for the PIR schemes we have implemented, it only supports reads, but for the ORAM-based solutions, reads and writes they just writes come for free. And I think for PIR it may take some extra effort if you want to support writes or general. Basically, there's also the more general question whether you can support general purpose computation. And the ORAM-based approaches, the first two approaches will support general purpose computation, whereas for PIR, the practical solution today doesn't support general computation yet. It's theoretically possible to support general computation, but it's like way out there. So I will do things in reverse chronological order. I will first talk about where things are today. Maybe hopefully you'll get more excited, and then I will tell you how we actually got here. The state of the art for the first approach, ORAM plus TE, so things are really fast. We can support key value lookup, and at 20 to 50 microseconds. So notice this is like not even millisecond level, it's microsecond level. Everything's on a single machine, and we are using like realistic data sizes, like from 100 gigabytes to 1 terabyte database, like for all of these experiments. Like exactly how large it is, it doesn't matter that much, like because for at least for 1 and 2, like the scaling is logarithmic. For 3, the scaling is square root n. So even though the data sizes like are slightly different for these experiments, it doesn't matter that much. Okay, we can handle 200K queries per second on a single machine. And I guess the state-of-the-art implementation is an implementation by our company. It's open source at this URL. So what about ORAM plus 2PC? And for this, the state-of-the-art is an open source implementation called picogram. The paper is not out yet, but the implementation has been out for a long time. It's open source. The paper is going to appear in Crypto this year. And you are looking at, so if you care about optimizing the online time, you are looking at about 30 to 40 millisecond online query latency for each memory lookup. If you care about total time, like let's say I care about the offline work as well, you are looking at roughly 300 to 600 millisecond per query. These two bars are not based off the same implementation. Like you need to make different optimizations to optimize for different metrics. And then PIR, the state-of-the-art is Piano, and I think Lin also has a paper. Maybe it has some slight improvement over these numbers. But I think all of this on the ballpark is like kind of the state-of-the-art. So this is really just dominated by the network latency. Like you are looking at total online latency about 100 milliseconds. But out of which, actually, in this experiment, 60 milliseconds is the just ping latency, the time it takes to even just send 0 bytes. So basically, the compute is only like 12 milliseconds per query online.
So for the first setting, what is the non-ORAM access cost? So let's say I use a TE and I'm querying, but I don't use an ORAM.
It will be a lot faster than 20 to 15 microseconds. It's like basically ORAM, it has like, you have to access this tree path, right?
Right.
So actually, I had this interesting discussion with Srini Davidis from MIT whether at this performance, it's still worth implementing ORAM in hardware. I think the answer is inconclusive. Like it may still make sense. I think at some point you need to consider the cost, whether it's cost effective to like actually implement ORAM in hardware or in software, because software can achieve like really fast performance already. So I think the answer is inconclusive. Like maybe it still makes sense to speed it up by implementing it in hardware, but it requires some further investigation.
So in the PIR numbers, you included the network latency?
This 100 millisecond includes 16.
In the microsecond example, you did not, right?
You mean picogram?
The first one, the TE.
Oh, this is just happening on the server side. So it's like on a single machine. But whereas, this doesn't include the time where the client sends the query to the server. It's just like assume the query is already on the server. So measuring the local latency on the server, whereas this is indeed taking into account the sending the query to the server. So that's where things are. I mean, you can see actually these crypto-based approaches are catching up. Like they have very promising performance already. Like you can even argue they can be deployed in applications that are not so performance sensitive. Of course, in performance-hungry applications, like, when we talk to, like, let's say the Flashbots, like they are doing it for block building, and when you talk to block builders, they'll tell you they care about 1 millisecond delay. So there, really, you want to use the TE-based solution. Okay, I also want to thank my students who did all this amazing work. And before I tell you how these schemes work, I want to ask a seemingly naive question, but actually maybe this is not a joke question. Perhaps like when I teach 451 algorithms to undergrads, like they'll be easily convinced that linear is no good and logarithmic or square root n is good. But actually when you talk to the more sophisticated audience, like cryptographers or real world practitioners who are implementing these things, they'll actually ask the same question, why don't we just do a linear scan? So why not? I can give you some concrete performance numbers. So Signal today, they're running ORAM plus TE. They have 6 servers. And their implementation is like, I think, about 20x slower than ours. And if you use a linear scan inside the TE with no crypto, that's what Signal actually tried back in 2017. And they were actually performing a highly optimized linear scan because they are doing batching and stuff. And they required 500 servers back then. And Signal also looked into performing a linear scan wrapped in crypto, like using classical PIR schemes. And they estimated the computing bill to be $300 million USD per year. So this also, I think there's also an interesting lesson to be learned from this, because latency actually is not the only metric you care about. Like for instance, like these classical PIR schemes can be easily parallelized, like they're trivial to parallelize. So you can parallelize the latency away, but you cannot parallelize the computing bill away. Okay. So for this reason, we perhaps like these linear solutions are not too great when you have these huge data sets. So in today's talk, I will tell you 2 extremely simple schemes, an ORAM scheme and a PIR scheme. And I unfortunately, I won't have time to tell you how to build a Garbled RAM, which is like the second category. Okay, so let's first start with ORAM. I will start with a little bit of history, how we actually got here. At the very beginning, in around 1986, there was hierarchical ORAM proposed by Goldrake and Ostrovsky. And hierarchical ORAM can achieve log cubed n, where n is the data size. It achieves log cubed n overhead. And they also prove a lower bound that any ORAM scheme must suffer from logarithmic overhead. And then there's a line of work that tried to optimize hierarchical ORAM. And there's a paradigm shift around 2011. We proposed this new paradigm called tree-based ORAM, and they're extremely simple schemes. And this is the kind of scheme I will tell you. You can get log squared n in theory, but actually in practice, it just behaves like a single log n, because these 2 log n's are not equal. Like one is a log base 2n, and the other is a log base something large n, and that log n is just like 2 or 3 in practice. And then, very recently, we've seen these large-scale real-world deployments.
The log squared is tight, at least in theory, right?
Log n is tight.
Oh, I see. So there are works that even in theory get log n.
There's works that we have a paper that actually gets log n, but I guess I think as of today, the practically optimal scheme and the theoretically optimal scheme are not the same. Okay, so I'll tell you how these tree-based ORAMs work. And before I do that, let's take a look at a simple strawman scheme. Suppose we are just going to permute the blocks in memory, like store each block at a random position, and then perhaps, let's say the memory, the adversary, like the server, doesn't know this random permutation. The advantage of this is like if I want to access any block, let's say I want to access logical block 9, I will just end up visiting a random location, and it seems like this should be safe to disclose. So what's the problem with this approach? The problem is like, it's okay if you just make one access, and in fact, it's even okay if you promise you are going to access each block at most once. So this is what I call one-time security. But once you start accessing the same block multiple times, you start to release statistical information. Like you can see frequency, and you can also see high-order statistics like co-occurrence. And these are very leaky, and you can perform statistical inference attack. So in fact, the reason why this approach is not secure is very similar to why deterministic encryption is not secure. And the lesson we should learn from this is that the blocks have to move around in memory. And in fact, every time you access some block, it has to move around instantly. So this is the key insight to keep in mind as we go over the scheme. So how does a tree-based ORAM work? Obviously, you're going to have a tree. Each node in the tree is called a bucket. Actually, in the ORAM community, like the biggest debate is not whether ORAM schemes are practical for large-scale real-world workloads. It's actually whether the tree is upside down or not. Okay.
I was about to say.
Yeah, this is a tree that you draw like as if you were a normal person, as opposed to a computer scientist. So.
Yeah. So inside each bucket, there's a finite number of slots. And And each slot can store either a real block or a filler block. So a real block is encryption of actual data, and the filler block is just encryption of 0. So the filler blocks are there just for security. And for now, you can imagine all the blocks are constant size, except the root. All the buckets are constant size, except the root bucket is like logarithmic in size. Okay, so the most important invariant is that every block is going to be mapped to a path. This means the block can reside somewhere on this path, right? So in this example, this block at logical address X resides on the blue path. And I will first cheat a little bit and assume that the CPU can store a large position map that remembers where every block is. I'll get rid of this assumption at the end. And I also want to mention that you should assume all the blocks are encrypted. And every time I access a block, I read or write the block, I will always re-encrypt it and write it back. So the server cannot tell whether I've changed the block or not. And the only thing the adversary can see is the access patterns because of the encryption. OK, so now reading a block is very simple. If I want to read block X, all I have to do is visit this blue path, read every block on this path. And once I find the block I want, I will hold it in my hand, meaning store it in some CPU register. And then if it is not the block I want, I just re-encrypt the same thing, write it back. If it is the block I want, I re-encrypt 0 and write it back to the same slot. So this is how we read a block. And at this moment, let's revisit the key intuition. Like after we read a block, it has to be relocated immediately. So how do we relocate it? The most natural idea is I will pick a new path and assign the block to a new path. So suppose I happen to pick the green path, and I want to write this block in my hand to this green path. And the question is, where on the green path can I write it? I mean, obviously, first I will update the position map to record the fact that the block has been relocated to the green path. And now I want to actually write it. And I want to decide where on the path I can write this block. So the first question is, like, can I write it to the leaf node? A lot of you have seen this already, and the answer should be no. Like, we cannot write it directly to the leaf node. And what's the reason? The reason is because if you just directly write it to the leaf node, you are declaring to the server, you're saying out loud, oh, hey, I've read something from the blue path, and now I'm writing it to the green path. So the next time, if you are requesting the same block again, you'll go to the green path, and the server can see the linkability. Okay, yeah, and now for the same reason, you should not write it to any of the internal nodes, because even though the internal nodes don't reveal the entire choice of the path, they reveal partial information about the choice of the path. So in fact, the only safe place to write it is into the root bucket. So okay, I'm going to take my block and write it into the root. The root is on every path, so it doesn't leak the choice of the new path. I guess I still need to address how I can keep writing things to the root, but let's set that aside for the time being. If I'm doing this, then security is easy to see. It's because every time I make a request, I will go to a random path. And importantly, the choice of the path has not been disclosed before. And this is because when I write it back, I always write it to the root. So I don't disclose the choice. And this is why the scheme is secure. And the only thing that's left to resolve is, like, I cannot keep writing things to the root because the root will become full. So how do I deal with that? There's a background maintenance process called eviction. And eviction is like trying to move things close towards the leaves to make sure no bucket will ever overflow. And a simple way to do eviction, this is the reason why the scheme is called path ORAM. So in path ORAM, the eviction algorithm piggybacks on the read path. So suppose I've just read something from this blue path. I will rearrange the blocks on the blue path to pack them as close to the leaf as possible. But just keep in mind, I cannot take any block on the path and write it into the leaf, because that may not be the leaf the block wants to go to, right? So I have to do this carefully in a way that respects the path invariant. So in some sense, path ORAM's eviction algorithm is the most aggressive eviction algorithm possible. Like, you're going to evict as aggressively as possible on the read path while subject to the path invariant. So we show that if the root bucket has size slightly more than logarithmic, and let's say all other buckets are constant in size, and actually 4 is enough. And then we prove that, except with negligible probability, no bucket will ever overflow. This proof is non-trivial. Even though the scheme looks like it's almost trivial, the proof is non-trivial. And thankfully, the proof is non-trivial, because otherwise, reviewer B would have said, your paper is trivial, reject, reject. Okay, yeah, this proof requires some sophisticated stochastic analysis of this randomized process. And there's only one last question left. I have cheated so far by assuming the CPU can store a position map. Yes.
What's the probability over?
You mean the sample space? It's over the randomness of in the algorithm. The algorithm is make these random paths, assigning things to random paths. So I need to get rid of the position map, and the solution is just one word. It's recursion. So I will take the position map, and instead of storing it in the CPU, I will store it in a smaller ORAM. And now I get an even smaller position map, and I recurse until the position map is constant size. So if your block size is large enough, let's say your block size is at least 4 log n, that means your position map is going to be a constant factor, at least a constant factor smaller than the original data set. So every time you can shave at least a constant factor off. So after at most log n steps, you'll get to constant size. So this contributes another log n. But the thing to keep in mind is that the block size in practice, like in SGX, it's like a page, it's like 4 KB. And in practice, the recursion depth is just 2 or 3 because the block size is reasonably large. Okay, so the total cost is log squared n in theory, but because one log has a large base, in practice, it's a constant. The algorithm is very simple. It's just a simple tree data structure. There's no cryptography at all. You are essentially just seeing database performance. This is not cryptography performance. It's just database performance. Algorithm can be described in 16 lines. Even if we count lines like NDIF and N4, you can print it on a T-shirt. I want to mention that when you implement these algorithms for real-world enclaves, you should not just take the path ORAM paper and implement as is. And the reason is because when we write these algorithms papers, we implicitly use the word RAM model, like including your algorithms textbook. Like there are like all these popular algorithms textbooks, and implicitly everyone uses the word RAM model. And here we assume like you have a CPU that talks to memory, and you are reading every cycle. You are reading 1 byte, reading and writing 1 byte, and we count the running time of the algorithm by counting how many steps it needs. Whereas in practice, we have a more sophisticated machine. Like for enclave architectures, what's important is that the page swap is a heavyweight operation. Like every time you perform a page swap, like you read and write 4 KB of data, even if you just want to read 1 byte, like it doesn't actually make sense for the enclave to try to fetch just 1 byte of data from outside the enclave just because of this high overhead of this context switch. In particular, what happens with the page swap is that you have to make a system call. You have to perform encryption and decryption. And if like the data is actually residing on disk, you also have to make disk swap. So this actually, in the algorithms literature, there's actually a whole line of work dedicated to this kind of computing model. It's called the external memory model. And in the external memory model, we care about not just optimizing the compute cost, but also they call it the I/O cost. And in particular, in this context, the I/O cost is the page swap cost. So you can take these ideas from external memory algorithm literature and optimize these ORAM data structures. And it actually makes a big difference in practical performance, because what you'll get is an asymptotical improvement in this external memory computing model. And this is one of the reasons why our implementation can outperform the others by a large factor. I mean, of course, we also have other algorithm optimizations. And also, actually, I want to mention our algorithm actually uses circuit ORAM rather than path ORAM. And this is because once we use these external memory algorithms to optimize away the page swap overhead, then actually the computation overhead becomes more important. Like if you don't do anything, your page swap will be like 90% of the overhead. And then we are kind of like, we can kind of balance the page swap overhead and the compute overhead. And we are at the point where we have to further optimize the compute overhead. And this is why circuit ORAM is better than path ORAM. And also, I want to quickly mention that not everything have to use an ORAM. Yeah.
So when you say compute overhead, we are talking about microseconds or nanoseconds at that point, because I guess at the register level, when you're accessing L1, it's going to be much smaller, right?
Yeah, so we actually also make I didn't say it explicitly, we also make our implementation doubly or strongly oblivious, meaning it's even oblivious inside the enclave. Even if you launch cache timing attacks, you cannot observe the access patterns within the enclave. So that that is the reason why we need circuit ORAM, because we need to, like in path ORAM, if you want to like make the eviction algorithm oblivious, right? You have to do these oblivious sorts on the path, and I don't know, we've written all these papers about that. But circuit ORAM, like what's interesting, like circuit ORAM was originally proposed for an MPC setting, but it turns out it's like useful for enclave. And I think Facebook also uses circuit ORAM rather than path ORAM. Maybe they realize the same problem.
So Elaine, are you saying the I/O is no longer the bottleneck?
In our implementation, it's kind of balanced because we made the I/O sufficiently small. Yeah. Yeah, I mean, like in practice, we can go into more details because in practice, like there's some difference between whether there's data residing on disk or everything is in RAM. Like this 20 to 15 microsecond is kind of like, it also captures when maybe even some things are sitting on disk. It's like maybe 15 microseconds. If everything is in RAM, maybe it's like more like 20 microseconds. So not all the time do you need an ORAM, because ORAM is like a generic compiler that can take any program and make it oblivious. But oftentimes, like you have these concrete data structures and algorithms that you care about, and you can do much better than generic ORAM. Like, there's a long line of work on this topic, like starting with oblivious data structures. And we also know like algorithms that are amenable to parallelization can be made oblivious without going through the generic ORAM transformation. Like, for instance, if you are looking at MapReduce and Spark, in the algorithms literature, this is called massively parallel computation, so a different kind of MPC. And you can actually transform an MPC program to an oblivious MPC program with constant overhead. So that log n even just goes away. And there's also like very nice work by Lin and David Heath, like this oblivious immutable memory model or the single access machine model, and they also can capture a large class of algorithms. So this is why in ongoing work, we are building an oblivious STL, which is kind of like oblivious counterpart of standard STL library. And we are going to ship these libraries with like highly optimized, customized oblivious algorithms. And to end this part of the talk, here's another large-scale application of ORAM. So they are available in Pittsburgh coffee shops. So if you come to visit me in Pittsburgh, I'll take you to one of these coffee shops and buy you an ORAM donut. Okay, so let me tell you how to construct private information retrieval. Again, this is going to be an extremely simple scheme. You almost don't need any crypto background to understand it. Okay, so how do we solve the PIR problem? One straw man solution, and this actually is an example of classical PIR, is to use fully homomorphic encryption. So imagine Tim is going to encrypt his query X, send an encryption of the query to the server, and the server homomorphically evaluates the query over the database and sends back encryption of the answer. And then Tim will use the secret key to decrypt the answer. And the problem with this approach is basically the bandwidth is ideal. It has constant or logarithmic bandwidth. But the server computation is very costly because the server has to take a circuit that encodes the whole database and evaluate the ciphertext using this large circuit. And that takes linear cost. So this whole approach, we can call it classical PIR. It was first proposed by Kaur et al. In 1995. And since then, there has been a line of work dedicated to studying classical PIR. And people have shown you can construct classical PIR, not just from FHE, but also from various other public key assumptions. But all of them suffer from the same drawback, like the compute has to be linear. And in fact, this is shown to be inherent, because if there's any location in the database you don't have to look at, then it reveals the information that the client is not interested in that position. I try to find a real-world application of classical PIR. I guess, of course, it has to be tiny scale. So I did find a tiny scale application. Google is using it to fetch device unique configuration while guaranteeing privacy. So this is like if you have Chromebook or something, like maybe there's like 100 different configurations and you want to find the configuration that fits your Chromebook. Okay. So obviously when you try to use it and for your large database, like Signal did the exercise and they were disappointed because it would cost more than 300 million USD per year. So in order for PIR to scale to large database, we have to rethink the problem definition. And Bimo et al., they proposed the pre-processing model in 2000. And the idea, so they proposed this model called server preprocessing. And in server preprocessing, you are going to take the database and compute some locally decodable code over the database, and which will make your query more efficient. And then there also has been a line of work dedicated to server-side preprocessing. And the latest is a groundbreaking result by Wei-Kai Lin, Lin, Mook, and Wicks. This won the Stock Best Paper Award, and they show we can do it with polylogarithmic bandwidth and compute, assuming the server expands the database into n to the 1 plus epsilon, where epsilon is an arbitrarily small constant. And they need ring LWE. So this result is very nice because theoretically it's dream, right? We cannot hope for anything better. I mean, maybe except if we can improve the server space, it would be nice. But concretely, it has astronomical constants, and it's like very, very far away from practical. So the question is like, can we actually have a truly practical PIR with sublinear computation, but without these heavy constants? So I want to talk about a line of work called client-side preprocessing. It was first proposed by, actually in two different works, like one by Patel et al. And the other by Corrigan, Gibbs, and Kogan. I think the Corrigan, Gibbs, and Kogan paper is more often cited because they actually made it sublinear, whereas like I think the Patel et al. Paper didn't make it sublinear. So I will talk about our scheme called Piano. I haven't explained what client preprocessing is, but actually it'll become obvious as I explain the scheme. It's a different kind of preprocessing. So what we can achieve is square root n cost. So square root n bandwidth and square root n compute with like square root n client space. And the only cryptography we use is pseudorandom functions. So that's why the scheme can be so lightweight. And this is actually theoretically also interesting because we know for classical PIR that doesn't do any preprocessing, this kind of result is not possible because any non-trivial classical PIR will imply public key cryptography. And another nice thing is that in this particular model, all of these trade-offs, like let's say the bandwidth and the compute trade-off is optimal, the bandwidth and the client space trade-off is also optimal under these assumptions. So we have like some lower bound papers, and there's also like some other lower bound papers earlier, like by Corrigan, Gibbs, and others. Okay, so here's how the scheme works. In the pre-processing phase, what do? We take this data set. It has n indices, and we'll divide them into square root n chunks, each of size square root n. And then we will sample one random index from each chunk. So this allows us to write down a set. We are going to sample a bunch of sets, and each set has one random index from each chunk. And this parity is defined as the database value at those indices, and then I XOR all of them. So I use parity of the set to denote this equation. So I will do this roughly square root n times, and I will write down square root n sets and their parities. And this is the information the client is going to obtain during the pre-processing. And that's why it's called client-side pre-processing. So besides this information, the client is also going to get some entries called replacement entries. And they're very simple. This just says for every chunk, I will pick polylog random indices, and I will store the database value at those indices. And these replacement entries will become useful later. Okay, so this whole thing is called a hint. And the client will start the hint, and it will facilitate the online queries. So if you do this in a naive manner, you can see the space is very large because to store each set requires square root n space, and I have square root n sets. So in this case, the client has to have linear space, and it might as well just store the whole data set. Fortunately, we can use PRF to compress them. Like instead of generating the set randomly, I will generate it pseudo-randomly. And this allows us to compress the space to square root n. And this is the only place where crypto will show up, and the rest of the scheme has no crypto. And basically, during the pre-processing phase, the client can write down this hint by making a single streaming pass over the database, and the client only has to have square root n space. That's why it's called a streaming algorithm. So it's not hard to see this. I will not go into details, but if you just think about it a little bit more, you'll realize how to do this. It's a homework exercise. Okay, let's go to the online phase. The client wants to fetch index 5. What does the client do? It will find a hint that contains this index, let's say the second hint, and it will find a replacement entry that belongs to the same chunk. Okay, so with this in my hand, I can now compose the query. The query is basically the set But I have to be a little careful because my query is 5, and I don't want to disclose that. So this position that corresponds to my query, I will replace it with this replacement entry. And remember, this replacement entry, this index is a random index within the same chunk as this position. Okay, so this is the set S star. The server just sends back the parity of the set. The client can compute the answer by just computing the simple XOR. This part comes from server's response, and these two comes from the local hint. You can easily verify this gives a correct answer. The security of the scheme is easy to see because this set S star just contains a random element from each chunk, and it's independent of my query because I did this replacement. Okay, so you might think, okay, we've solved the problem, but actually there's a catch because the scheme so far works only for one query. If you make more than one query, it's not secure. And do you know why?
It's like a one-time pad thingy where if I have two things, I can XOR them and get it.
Not exactly. So the question is like, once I consume the hint, what do I do with it? Like I have this database of hints and I consume one of them, right? Maybe the most natural way is to delete it. But the problem is like if I delete it, then it skews the distribution of my hints. Like the remaining hints are slightly less likely going to contain 5. And that makes the new queries slightly leaky. I mean, you also cannot just leave it there because if so, like the next time you use this hint, it'll end up leaking information. Okay, so that's slightly problematic. And how do we fix this problem? So in order to support more queries, I will introduce a simple technique called broken hint technique. And the idea is really simple. Once I consume a hint, I'm going to throw this hint away, but replace it with a random hint subject to containing my query 5. Because if you think about it, the distribution of this set is a random set subject to containing 5. So I just have to sample a new random set subject to containing 5 and replace the consume hint. Yes?
Is it the same idea as what you have in a hierarchical ORAM level? I think you access one and then you replace it by some. The next time you kind of ensure that you're not accessing the same thing.
Maybe there are too many hierarchical ORAMs. Maybe it's like.
I mean, the original Goldrick-Ostrowski one.
I think they have like one time. They require one
time memory.
Access each location only once.
Right. So this is not using something similar. Okay.
Maybe there's a way to view it such that it's similar, but maybe we can discuss it offline. There are too many different hierarchical ORAMs. Okay, yeah. So the only problem is like I'm replacing it with this random set, but I don't know the parity. So what do? I will just mark it as broken and hope that I don't hit it the next time. If I do hit this entry the next time, I will not be able to obtain the correct answer. So I lose in correctness. So this has allowed me to transform security error into correctness error. And to fix the correctness error, I just need 2 words, parallel repetition. I'm going to repeat the scheme like roughly logarithmically many times. And it'll if you repeat it like super logarithmically many times, you can amplify the correctness failure to negligibly small. In practice, you don't actually have to even suffer from the parallel repetition overhead. You just have to do some additional trick to get rid of the parallel repetition overhead, but I won't go into the details. You can read our paper. So the scheme so far, just to quickly summarize, in the pre-processing phase, the client makes a streaming pass over the whole database, consuming square root n space, and it'll record a square root n size hint in roughly linear time. Online query, client sends a set to the server of square root n size. The server sends back a single parity. Client computes the answer. So extremely simple. There's just one last thing I want to mention. The scheme so far supports only square root n queries. So let's assume the database has been randomly permuted. So every time I query a distinct index, it's going to land in a different chunk. And I've said, I prepare polylog replacement entries per chunk. So after I throw these square root n queries into square root n chunks, with extremely high probability, I'm not going to be able to I will not run out of replacement entries. But if I make more queries, I may eventually run out of replacement entries. So how do we extend this bounded scheme to unbounded? And that's just one word we can do: pipelining. Basically, we are going to run the next phase's preprocessing in the current window of square root n queries. And you can see that because this pre-processing cost is linear, amortized to square root 10 queries, it just introduces square root and overhead for each query, which we already incur anyway. So if we implement the scheme and compare with classical PIR, we are like about 900x better in compute than classical PIR. So the actual response time, this number is diluted just because it's like already ping latency dominated. Like in this experiment, the ping latency is much larger than the compute overhead. Okay, so I will try to end and talk about some open questions. But before I do that, like I haven't had time to talk about this 2PC, ORAM plus 2PC. I will just quickly talk about how we got here without going into any technical detail.
Elaine, the PIR, this is honest but curious adversary or malicious?
The server can, if the server is malicious, it will harm correctness, but it doesn't learn any. Privacy is against malicious server. Yeah. Okay, so before I ask open questions about ORAM plus 2PC, let's quickly look at how we got here. So there's practical land and there's theory land. In theory land, RAM model 2PC was first proposed in 2012 in a paper with many authors by Gordon et al. And then Garbled RAM was proposed like around 2014-ish. The difference is RAM model 2PC is like doesn't care about the round complexity. If you have a computation that runs in T rounds, the RAM model 2PC will give you a protocol that runs in T log n rounds. So it's very, very interactive. And this Garbled RAM requires it's only 2 rounds. No matter how long the original computation is, you can only have 2 rounds. So it did not take very long before we made RAM model 2PC practical. And this is actually when Kartik was a PhD student and we were all happily doing research in Maryland, we like worked on all of this. But it took much longer for people to make Garbled RAM practical. So Kartik will be happy to hear now, actually, there's a new state of the art for RAM model 2PC, which is our new Garbled RAM. But I also want to mention that we are also building on others' work, like the work by Heath et al. So I think this is, in some sense, both encouraging and a little bit disappointing. It's encouraging that we've made a big step forward since 10 years ago. But on the other hand, I feel like there's very little work on RAM. And that's why when I was like looking for a baseline to compare to, I was surprised that even my own work 10 years ago is still like a baseline, is like the state-of-the-art baseline. Okay, so on the theory front, there's more like fancy algorithms, 16 Garbled RAM and RAM model FHE. I will tell you what they do. So essentially, Garbled RAM, the bandwidth is not succinct. Like if you have a computation that runs in T time, you would have to consume roughly T bandwidth, whereas in theory, you can compress the bandwidth to almost constant, like polylogarithmic, but you need like some stronger assumptions like indistinguishability obfuscation or ring LWE. And I think the interesting question is like whether any of these theoretical techniques can be made practical. So this is also like one place where theory starts to diverge a little bit from practical, because in practical, we don't really care about just minimizing one metric, like at the cost of, let's say, compute, right? Like what we care about is just the end-to-end time. And in some sense, it's like the bottleneck cost that we care about. Like really in practice, when we implement these things in practice, we'll always try to balance the bandwidth costs and the compute costs. But that's not saying like these theory things we cannot use the techniques from these theoretical works. So I think the exciting open question here is, can we take any of these techniques here to design a practical Garbled RAM or RAM model 2PC or MPC technique and that achieves actually better concrete performance? So you can break this question down into more finer grained questions, but I'm not going to try to do that here. So let me talk about open questions along the PIR side. So this actually comes back to what Itai was asking earlier. So in PIR, like even though it looks like the performance is similar to Garbled RAM, there are a couple of drawbacks. Like one is the practical implementations today only support retrieval. It doesn't support general purpose computation. If the database is updating very, very fast, like in blockchain scenario, like the updates are much, much faster than the queries, and then you have to pay, every client has to pay per update, which makes things more messy in practice. So I think, whether we can overcome these drawbacks are interesting open problems. But I do want to mention like PIR has one advantage over RAM model 2PC, which is like the trust model, because this PIR, you can do it with one server, whereas the 2PC, you need two servers. Okay, so here are some interesting open questions. Can we make it work for fast evolving databases? And one reason why these client-side preprocessing schemes are not compatible with fast evolving databases because the client has to be involved with the updates. So perhaps like we can try to make server preprocessing approaches more practical. That's interesting question. And if you want to support general computation, like it would be more like making RAM model FHE practical. And again, you can break these things down into smaller questions, but I will not try to do that. Okay. So I gave this talk in Simons. That's why this is measuring time in terms of Simons. So I want to just quickly say where we were, where we are, and where we want to be in Simons 2035. So, okay, the Simons 10 years ago, like I was giving talks about tree-based ORAM. And then this most recent Simons, we see ORAM has large-scale practical deployment. So I think as far as ORAM and PIR involved, we want to actually make this more widely deployed, have more open source libraries to support people's development efforts. Or perhaps you can also be more hopeful and ask, in 10 years, we don't want TE anymore. And this is why we want to have 2 and 3. So 10 years ago, as I mentioned, for Garbled RAM, for RAM model 2PC, the state of the art was like these more interactive protocols. And then for PIR, we started with classical PIR. So I'd like to think that today we are kind of like at the similar paradigm shift for these other, because this was like a paradigm shift that made the practical deployment possible. And I'd like to think that we are kind of at a similar paradigm shift today. So hopefully 10 years later, we can see large-scale deployments of these technologies as well. I want to mention there's actually things beyond cryptography that are really important for this line of work. Like one is crypto meets programming languages. And this includes not just formal verification, but actually language design and optimizing compiler is very important. You want to make it easy for people to program these things. And also, instead of a posterior formal verification, actually using type system and information flow to just catch possible mistakes a priori, I think this approach will have a long way to go, yeah. Okay, and crypto meets algorithms is also I think, interesting intersection that is often overlooked because there's a lot of work that's trying to make crypto practical these days, and a lot of them actually requires algorithms techniques. Like for instance, I talked about one example of using external memory algorithm techniques in the context of ORAM, but there are many examples like this, like people are trying to parallelize cryptography, and there's a lot of interesting techniques in the other MPC literature, in the massively parallel computation literature that are potentially helpful. And another interesting connection is crypto has a different model of computation. Every different crypto, HSS, homomorphic secret sharing has its own computation model. MPC has its computation model. ZK has its computation model like R1CS. And we actually don't understand algorithm design in these crypto models of computation so well. We don't have a good understanding what tasks can be programmed efficiently in these models. Okay, yeah. Thank you very much.
Can you explain again the use case in the blockchain setting? Are we doing a PIR over the entire ledger or some over the
There are
state?
both use cases. For instance, if let's say I just want to make a Uniswap transaction oblivious, then you only need to do it for the part of the database for Uniswap transactions, like all the Uniswap accounts. But more generally, for instance, Vitalik wants this built in the RPC node, alchemy, inferior, Geth. So this would just be enabling it for the entire blockchain. I think we'll start from the state because the state, I think, is queried more often than the ledger. But potentially, we can do it for the ledger too.
I see. Then do you know, roughly speaking, on what order of magnitude that size is?
I believe the ledger is maybe on the order of...
Ledger is the 1 or 2 terabytes. But
the state I think is on the order of 100 gigabyte some hundred
Maybe 300
gig,
gigs, something like
300
Okay.
gigabyte.
that. Maybe
I
something
see.
like that.
So because we also have reasonably fast linear PIR right now, and that's maybe 1 gigabytes per second in terms of processing speed. So if it's a 100 gigabyte database, we need 100 seconds. So that's still
Actually, if you can give me like a cost, I think Signal cared more about the cost for linear PIR. Yeah, because for them the problem was like 300.
right. But they're probably
million
comparing
USD
to
per
these
year.
number theory based ones, right? Using the lattice based ones, it's at least 1000x better than that.
Yeah, if you have actually updated measurement number for that, I think so Signal's number was taken using the state-of-the-art scheme in 2023, so it's like two years old.
I have a broad question. So, from a practical standpoint, how important do you think is it to work on improving ORAMs and ORAMs and making them practical versus improving Oblivious algorithms, specific Oblivious algorithms?
That's a good question. Like, I think we need both because there are applications that just need ORAM or Oblivious key value store. Like for instance, Ethereum, Signal, Matter. Like I think they need an Oblivious database. But what's interesting is like while they are developing this Oblivious database, like Signal, for instance, they want to make it distributed. And when you start doing these things, you'll end up needing like Oblivious sort and like these Oblivious building blocks. So I think like they go hand in hand. Like even if you just want to optimize ORAM or distributed, let's say Oblivious key value store itself, you need to use like some primitives from Oblivious STL. Yeah, and I think we are also like, we did all this compiler work in UMD. We are also trying to now make them like commercializable, like production ready. Because I think a lot of the times, if let's say you have a customer that just wants some specific computing task, like you had this nice word graph SC, right? Like for a lot of these parallelizable computing tasks, we don't need ORAM. We just need Oblivious sort.
Maybe quick comment following up on Ling's question. I think there are ORAM light client protocols, right? Or I've heard light clients.
I think there's a company also besides our company. There's also another company called Automator, and they're saying they want to do ORAM. I don't know. I haven't seen an actual implementation from them yet, but I think it's also on their agenda. So I think Ethereum is also talking to them as well.
Right, because I've heard some discussions. Not sure what's the state of the art or if it's.
I haven't seen their implementation, but they have been saying they want to do ORAM. Yeah.
I noticed that there are some data access protection paper under relaxed notion called differentially private obliviousness. Do you think how does that help to make the data access pattern project more realistic? And do you think this notion makes sense?
No, actually, differential obliviousness can be important because a lot of times. So I think differential oblivious is most important when your worst case cost is very large. And in practice, you don't want to suffer from the worst case cost. Like let's say for database joins, like the worst case cost is quadratic. And if you want to be fully oblivious, that means you have to be quadratic. Whereas in practice, like most of the common queries in practice are just linear or quasi-linear. So in these cases, you want to kind of pad it with some noise. So you actually just see quasi-linear overhead in practice. So that I think is not just a log factor difference, it's a polynomial factor difference. So even when we are working on these oblivious implementations, like I was talking to some company providing cloud service yesterday, and they want to build ORAM into container, like let's say make the file system layer oblivious, and there, if you are doing it at the file system level, there's going to be some leakages about the file length. And that I think you can secure with these differentially oblivious techniques.